Hi everybody, I hope this video finds you well. In today's video, we're going to be taking a look at section 1.10 from your textbook, which is a quick introduction into approximating solutions to first-order differential equations. As the name would imply, this section is all about coming up with numerical approximations to solving first-order differential equations, specifically first-order differential equation IVPs. This section is sort of similar to sections that you probably saw in your Math 190 or 191 course. In 190, you learned how to do some linearizations, approximations to the derivative. In 191, you saw how to do like a numerical integration where you were able to approximate the area under a curve using left endpoint or right endpoint approximations. This sort of section is a brief introduction into a similar idea for differential equations. So the idea here, again, is going to be that we want to be able to sort of approximate numerically, so just using sort of arithmetic computations, the solution to a differential equation and avoid actually having to explicitly solve this differential equation. Now, it turns out that in general, if we were taking a full class in differential equations, in other words, if our class was not split between linear algebra and differential equations, and we had an entire semester just to dedicate to differential equations, we would spend a lot of time learning about ways to approximate solutions to differential equations. And the reason that we would spend a lot of time doing that is because, as we've seen, it's pretty hard to solve differential equations, right? So far, we've only learned how to solve differential equations in very specific situations. So actually, in the broader scope of things, coming up with numerical solutions to differential equations is a very, very sort of important field of study. There's entire classes dedicated to just better and better ways of approximating numeric solutions to differential equations. Your book goes through several different methods for doing these approximations. I believe that they talk about the Euler method, which is the one we're going to discuss. They also talk about like a modified Euler's method, a Hune's method, and a Runge-Kutta method. Those are all great ways of coming up with approximate solutions, and they're all very sort of interesting. Unfortunately, though, they're a little bit outside the scope of our class, just because in our class, we're not really trying to make too much use of calculators or especially like mathematical software, which is what you should really have when you're trying to do approximate solutions. So we're only going to look at the most basic way to do this approximation called Euler's method. So that's the only part of the section 1.10 that you guys are sort of responsible for, just the Euler's method. So what is Euler's method? Well, Euler's method basically extends the concept of linearization that you learned from differential calculus, the idea of sort of taking the moment or the approximation of the derivative at one particular point and then extending linearly from there to come up with an approximate solution to an IVP. So we're going to state Euler's method, give a quick visualization, and then look at a couple examples. So Euler's method can be stated as follows. So we're going to suppose we have an initial value problem that we've written it into the form y prime equals a function of x and y, which, you know, this form is something we know we can do for any first order differential equation. We can always isolate the y prime and then write everything as a function of x and y. And then with the initial condition, y of x sub 0 equals y sub 0. So this Euler's method applies to solving an initial value problem. So it's got to have a differential equation and an initial condition. Then what we're going to suppose is that we're going to define x sub 1 to be x sub 0, the original x value, plus h. And h is usually referenced in Euler's method as the step size. It's basically how far forward you're going to advance on your solution curve. Then, in our notation, we could say that y at x sub 1, so the y value at that corresponding x sub 1, which notationally could be just written as y sub 1, will be approximately y sub 0, the initial y value, plus h times f evaluated at x sub 0, y sub 0. So why does this formula sort of make sense? Well, it's basically saying that y sub 1 will be the original y value plus the step size times the derivative, because what is f at x sub 0, y sub 0? Well, that's the derivative evaluated at that point. So in other words, to figure out what the next y value is, you basically take the previous y value and then add to that the step size, how far are you going, and at what approximate slope are you going at. In general, we can say that if x sub n is equal to x sub n minus 1 plus h, so we're always advancing the x by this step size of h, then each of the corresponding y values is approximately the previous y value plus h times the differential equation evaluated at the previous point. So the visualization of this is very simple. Let's imagine that we have some sort of axes, and say we have a sort of solution curve. So there's our solution curve. And say we happen to have the initial condition, say maybe we'll say right there for fun. Right? And so let's call that our x sub 0, y sub 0. So what we're sort of imagining here is that we do not know what the equation of the solution curve is. So we don't know what the solution curve looks like or the equation of it or anything. We just know that we happen to be on it right at that initial condition. What we're trying to say is if we wanted to figure out what happens, say, at x sub 1, where the gap here is h, right? So we're trying to approximate this value right here, right? Which would be y sub 1, right? We want to try to approximate this. This y sub 1. So what our goal is that because we have this differential equation that tells us based on x and y what the derivative is, we are able computationally to figure out the derivative at this particular moment. In other words, we can come up with the tangent line at this point, and we can extend that tangent line in both directions. Then what we're saying is if we follow that tangent line, whatever that tangent is, for a distance of h, right, we will follow it along right to there. And that right there will be our approximation. And of course, it's not perfect, right? You'll notice that in my drawing, assuming that the curve is concave up over this thing, my approximation is going to be an underestimate. But the idea is if you make that h very small, so if you make the step size very, very small, then this approximation will be much more accurate, right? If I had done it here, then I would only need to follow here and the gap would be much smaller. Obviously, with a sort of computer or some sort of software, you could do the step sizes in incredibly small increments and have a very good approximation using this method. So this is sort of the idea. We're going to take our initial value. We're going to use the initial value in the differential equation because the differential equation literally gives us a relation to know what the value of the derivative is. Once we know the value of the derivative, we can have our sort of tangent line there. Then we follow our tangent line over the course of h. That means we move up by a factor, or move up or down, I suppose, if the slope is negative. But we move up or down by a factor of h times that derivative. That's where this h times the differential equation comes in. We add that to the original y sub 0, and that gives us our approximation. So that's the visualization for this Eulers method. More advanced methods like that Eulers method, the Runge-Kutta method, the modified Eulers method, basically just try to make this approximation even better. There's methods where you sort of do, you make an advanced point, then you sort of find an average in between, you use that as another approximation, and you modify your approximation, which can be much more accurate. Some of them use several points to interpolate instead of just 2 points like this, so on and so forth. But again, only the Eulers method is really going to be part of our course here. So this is the only method you guys have to know in terms of numeric approximations. Okay, so let's go ahead and take a look at running this method on a very basic differential equation and comparing it against the solution that we could actually find by using our techniques. So let's take a look at our first example here. So we're going to consider this very basic IVP, y prime equals x minus y over x, with the initial condition of y of 1 equals 2. So this is an IVP. What we're going to do is we're going to use Eulers' method with a step size of 0.25 to determine y of 2. Then we're going to solve the IVP directly, because this is a pretty easy IVP, and directly evaluate y of 2 and cross-compare. And we'll just see how accurate it comes out. We're not expecting it to be incredibly accurate because, I mean, 0.25, that's a pretty large step size still, but let's just take a look. So for A, let's have a nice way of sort of writing this up. We have our y prime is x minus y over x, so that is in the correct format, and our initial condition is y1 of 2. So I like to make a little table. So there's going to be my n, and n sub 0 is going to be my initial. So we have x sub n and y sub n. So x sub n and y sub n are going to be your initial condition. So my initial x is 1 and my initial y is 2. So you can sort of see x sub 0, 1, y sub 0 is going to be 2 here. So now we're going to take a step forward. So this would be n equals 1. What is going to be our next x? Well, we move forward by 0.25, so this would be our approximation at x being 1.25. And now we need to find our next y value. So to do that, what we're going to do is do 2 plus the differential equation, which I'm going to write as f, meaning this thing here, evaluated at this previous moment. So evaluated at 1, 2. So, and we got to get our h in there. So we got to have our h, which is 0.25, times our differential equation, evaluated at 1, 2. So we're saying we start with our initial y, we move forward by our step size of 0.25 times whatever our slope is. How do we actually determine this? Well, we just plug this into here. So we're doing x is 1, y is 2. So it looks like that would be 2 plus 0.25. F 1, 2 is going to be 1 minus 2, which is negative 1, divided by 1. So it looks like we get minus 1. And then we get that is going to be 1.75. And in a moment, I'm just going to start using a calculator. So I'll probably just keep decimals, and I'll probably just keep like 2 or 3 decimal places. Again, we're not going to worry too much about like anything like significant figures. We're just trying to get the general idea here. So we're saying that if we're looking at the solution curve, which has the solution to this differential equation with this initial condition, we expect that at 1.25, it goes through about 1.75. Now we'll take another step forward. So we'll go to n equals 2. That means we're moving to our approximation for at x equals 1.5. We'll take our previous y, 1.75, plus the step size times f at this previous one, which would be the 1.25 and the 1.75. So 1.25 comma 1.75. That's going to be 1.75 plus 0.25 times, and now I'm going to have to plug this 1.25 and 1.75 in there. So I guess that would be 1.25 minus 1.75 and then divided by 1.25 because that's our x. Looks like we should get minus 0.4. So we'll get minus 0.4 there. And then if we put that together, 1.75 plus 0.25 times negative 0.4, looks like we should get 1.65. So our approximation is that at x equals 1.5, y should be about 1.65. Okay, we'll take another step forward. Remember, we will want to get our approximation for y of 2. So we have 1.75. Now we take our previous y value, so 1.65, plus 0.25 times f, evaluated at our previous x, which is 1.5, and our previous y, which is 1.65. So it's going to be 1.65 plus 0.25. We've got to plug these guys in there, so we get 1.5 minus 1.65, and then divided by 1.5. And looks like we should get negative 0.1. Okay, so 1.65 plus 0.25 times negative 0.1. Looks like we should get 1.625. Okay, now our last approximation at 4. We're going to go for x is 2 now, so that we've taken 4 steps forward. We take our last one there, 1.625 plus 0.25 times our function at our previous step, which was 1.75 comma 1.625. Again, grabbing the previous x and the previous y. That means we're going to have 1.625 plus 0.25. Plug that stuff in, 1.75 minus 1.625. Divided by 1.75. Okay, it's going to be sort of an ugly decimal there, so I'm just going to put 3 decimal places, 0.071. And if we put that all together, 1.625 plus 0.25 times 0.071, looks like we should get 1.643. That's sort of our rough final answer there. And again, that is just an approximation, especially since I started rounding there. So that's approximately 1.643. Okay, so my approximation tells me that at x equals 2, my solution curve is at about 1.643. Notice it was sort of interesting, right? The first couple steps, our population or our y value was declining from 2 to 1.75 to 1.65 to 1.625, but then right at the end it sort of peaked back up a little bit. Let's compare this to how accurate it actually was if we just solved it directly. So let's solve this thing directly, y prime x minus y over x. With y of 1 equals 2. May not be initially clear how we want to, but notice, I mean, there's nothing too weird with y here, so we might actually suspect that this thing is linear. It actually is, so let's see if we can do that. It's going to be 1 minus 1 over xy. Notice we can bring this over onto the other side to get linear standard form, so y prime 1 plus xy equals 1. And then we can use our integrating factor approach. So the integrating factor here is e to the integral 1 over x dx, which is e to the ln x, which is going to be just x. So let's multiply both sides by x. So we get xy prime plus y is equal to x. We'll go ahead and solve that over here. The left-hand side has to be a product rule, so it's xy prime is equal to x. Integrate both sides with respect to x, so xy is the integral of x dx. xy is 1/2 x squared plus c. And divide by x, I guess we get 1/2 x plus c over x. We can pop in our y of 1 equals 2, so we get 2 equals 1/2 plus c. And it looks like c should be equal to 3/2. So our unique solution here is y equals 1/2 x plus 3/2 over x. Okay, now can we evaluate directly? Well, yeah, we can say, okay, y, if we want to, y of 2 would be equal to, well, if we plug in 2 in there, we'd get what? 1, and then 3 over 2 divided by 2, so 3 over 4. So it looks like 1 3/4, which would be 1.75. So the actual value of the solution curve at y equals 2 is 1.75. Our approximation came up with 1.643. That's not super close. I mean, it's off by about 0.1, which is not so great when you're only measuring things that are about 1.5. I mean, that's a little less than like a 10% sort of error. But again, we did this, I mean, basically in only 4 steps. I mean, we did our moves as only 0.25. That's a very sort of large step size. So, I mean, the level of accuracy is not expected to be super high here. I just wanted you guys to be able to sort of cross compare here versus what actually happened in solving it. Obviously, in real-life situations, this part is not something we're interested in doing because the reason we would use a numeric method is most likely that there isn't an easy way to solve it directly. So this numeric method is usually just done by itself, but I wanted you guys to see at least one time where we used the numeric method and then we could compare it against what actually happened by solving the differential equation. So that's our first example of running the Eulers method. As you can see, it's pretty direct. It just basically involves plugging in the previous steps from your approximation into your differential model. That gives you the slope. You use that slope times your step size, and then you allow that to be added onto your previous y value to get your next y value. Okay, let's take a look at running this Eulers method a second time, but on something that's a little bit more interesting, something that we definitely would not want to try to solve directly, and tying this in with some of the modeling that we did earlier, specifically with some of those more interesting population models. So we're going to suppose that we have a population of fish that is growing when left alone, according to a logistic growth model. Remember, a logistic growth model means a growth model where the population grows at a rate proportional, in this case with constant 1/12, to the product of their current population in thousands and the difference between their current population and the carrying capacity of the lake they live in, which is 5,000. So remember, logistic growth basically says you grow proportional to how many there are and the amount of sort of room that's left, carrying capacity minus current population. We're going to further suppose that these fish are being harvested initially at a rate of 250, or since we're going to measure everything in thousands, 0.25 thousand per year. But the harvesting is increasing by 100 or 0.1 thousand per year. So the rate of harvest is increasing over time. So it's not just a constant harvest. How many are being harvested each year is actually going up. Finally, we're going to suppose that the initial population of this fish in this lake is 3,000. So we have it as an IVP. We're going to try to write down an IVP to model this, and then, since it's a pretty messy one to solve and it does not have easy equilibriums because of the fact that their rate of harvest is non-constant, we're going to use Eulers' method with a step size of 0.5, or if you prefer, a step size of half a year, to approximate what's going to happen to the fish population in 3 years. So let's go ahead and begin by trying to write down our IVP. So we're going to have to talk about dp/dt, the change in the fish population with respect to time, treating the population here in thousands and time in years. So we're told that it has a logistic growth model, and we're told that the constant of proportionality is 1/12, so we know we're going to have 1/12. And then the logistic growth model is the product of their current population. Current population is our variable p. And the difference between the current population and carrying capacity. So we know that that should be 5 minus p, because the carrying capacity is 5,000. So we put the carrying capacity first so that if p is ever greater than 5, then this whole thing will become negative and our population will decline. So there we go. There's the logistic growth part. And then we know that they're being harvested initially at a rate of 250 or 0.25 thousand per year, but the harvesting is increasing by 100 per year. So we're going to have a minus, and then in parentheses, if it was constant, we would just have our 0.25. But we know that in 1 year, it's going to go up by 0.1 thousand, and then another 0.1 thousand, so on. So we should have 0.1 t. So notice you can sort of imagine, like if you look at the discrete times, at t equals 0, this would just be minus 0.25 because they're losing 250 per year. But at t equals 1, it'll be 0.35 because they're losing 350 per year, so on and so forth. So there we go. There's our differential equation for this. This would not be a super pleasant one to try to solve manually because, as we can sort of imagine, it's not separable and it's non-linear, so it gets pretty messy to do. Also, our equilibrium approach doesn't really work because if you try p equals a constant, well, this part will reduce into constants, but this will be in terms of t, so there are no equilibrium solutions. So this is sort of the best we can do here. In terms of an initial condition, we have that p of 0 is equal to 3, because again, we're measuring everything in thousands. Now, the main thing we want to do is avoid trying to solve it and use this Eulers method with a step size of half a year, or 0.5, to approximate what happens to the fish population in 3 years. So let's go ahead and do that. We'll make our table. There's going to be our n. Then I guess we're going to have our t sub n, which is going to stand in for x, and then we're going to have our p sub n, which would stand in for y. So our initial one at n is 0, which means that t is going to be 0 and our population is going to be 3. Along the way, we're getting information, so it's not just important what happens in 3 years. This will also tell us what we sort of expect to see happening every 6 months or so as we check in on this. Okay, so at n equals 1, we're going to advance our independent variable by the step size. So we're now going to be at 0.5. And then this will change to taking our original population, 3, plus the step size, which is 0.5, times our differential equation evaluated at the previous moment, which is 0, 3. Now, what we'll need to do is we'll need to plug t equals 0 and p equals 3 into this. So if we do that, we should get 3 plus 0.5, and I'm just going to go ahead and sort of do this on the calculator. So we'll have 1 divided by 12 times 3 for p times 5 minus 3, and then we'll subtract 0.25 plus 0.1, and then for t right here, we'll plug in the previous t value, which was 0, so 0.1 times 0. You put all that in, and we should get a 0.25. So in that at that first moment when the population is 3,000, notice that they're below the carrying capacity. This is growing. They're sort of outrunning the amount that's being harvested because only 250 are being harvested. You guys can actually check that manually. When p equals 3, you're getting 3 times 2, which is 6, divided by 12, which is a half. half of 1,000 is 500. So the population's sort of growing at 500 fish and only 250 are being harvested. So the population is currently growing at a rate of 250 fish per year. We're only running it for half a year though. That's why we're at times 0.5. And if we put that together, 3 plus 0.5 times 0.25, we'll see that after 6 months or after half a year, we expect the fish population to be about 3,125 or 3.125 thousand. Okay, now we'll advance another one. So this is n equals 2. So this would be what we expect in 1 year. So 3.125 plus 0.5. And now we're going to evaluate our differential equation at 0.5 for t and 3.125 for our population. So that's going to be 3.125 plus 0.5. And now I'm going to be plugging in 3.125 in for p and 0.5 in for t. So we should get 1 divided by 12 times 3.125 times 5 minus 3.125, and then minus 0.25 plus 0.1 times, and we're plugging in 0.5 for t, the previous t value. And once we do that, we should get that this comes out as about 0.188, again rounding to just 3 decimals. All right, so population still growing. Notice that after the 6 months, there's going to be a little less growth, which should make sense because we know that the harvest rate is increasing. And also we know that once there's sort of more fish, since we had some growth initially, that means because we're getting closer to the carrying capacity, the growth in the population should also be decreasing. So it makes sense that we're seeing less growth as we sort of go on. Putting that together, 3.125 plus 0.5 times 0.188. We should see that we now have about 3.219, so about 3,200 and some fish. Okay, let's move forward again. So we have n equals 3. Now we're at a year and a half in. So we have 3.219 plus 0.5 times our function evaluated at t equals 1 and p equals 3.219. So that's going to be 3.219 plus 0.5. Now again, plugging this in for t and this in for p. So 1 divided by 12 times 3.219 times 5 minus 3.219, and then minus 0.25 plus 0.1 times the previous t, which is 1. And looks like we should get about 0.128 there. So again, the growth is slowing even more because we know the harvesting is going up and up. And we know that this, because we're getting a higher and higher population, is also slowing because we're getting closer to the carrying capacity. 3.219 plus 0.5 times 0.128 means that we're now up to a population of about 3,283. Okay, we'll advance again. Now we're at the 2-year mark. So we have 3.283 plus 0.5, f of now 1.5, previous t value, and 3.283, previous p value. So that's going to be 3.283 plus 0.5 times. Plug this stuff in. Once again, this going in for p, this going in for t. So 1 divided by 12 times 3.283 times 5 minus 3.283, and then minus 0.25 plus 0.1 times our previous t, which is 1.5. And now we have a very small sort of growth. It looks like when we round, we get 0.070. So 3.283 times plus 0.5 times 0.070. We get up to about 3.318. So about 3,300 some fish at this point. Okay, we advance again. We're almost there. 2.5, 3.318 plus 0.5 times f at 2 and 3.318. So we get 3.318 plus 0.5. And then we're going to plug in our 2 for t and 3.318 for p. So 1 divided by 12 times 3.318 times 5 minus 3.318. And then minus 0.25 plus 0.1 times 2. And looks like we have almost no growth now. It's going to be 0.015. So 3.318 plus 0.5 times 0.015. Looks like we should get 3.326. So very, very small increase. And then we get our last one, which is going to tell us what we should expect in 3 years. 3.326 plus 0.5, f at 2.5, 3.326. Looks like we should get 3.326 plus 0.5 times. We plugged in one more time. So 1 divided by 12 times 3.326 times 5 minus 3.326 minus 0.25 plus 0.1 times our previous one, which is 2.5. We get a negative, so now the population is starting to decline, negative 0.036, and we get 3.326 minus 0.5 times 0.036, and looks like we should end at about 3.308. So what we would say is P of 3 should be approximately 3.308. So after 3 years, approximately 3,308 fish in lake. Now, as we can imagine, there's probably going to be, if we continued on doing this, I think that's enough calculation for now, but if we continued on doing this, we'd probably see some more negatives because we know that that rate of harvest is just going to keep going up and up. Of course, though, as the population starts to decline, there might be a slight increase in at least the growth component. Not sure that that would make up for how much larger the harvesting is going to become each time we advance. So we'd have to continue analyzing if we wanted to know whether or not the population would sort of cycle around, become stable, or maybe tend towards being extinct or something like that. But notice that even though we're unable to sort of go through and solve this one directly, at least we can actually go ahead and get an approximation for what's going to happen sort of down the line. Certainly, if we were using computer software, we could do a much smaller step size and we could go much further out and still get a very sort of accurate picture here. So numerical approximations are a very important idea in differential equations as a subject. For our class, though, only this Eulers method is going to be something that you might run into, and really just going to make sure you're comfortable setting up and running through at least a few of these computations. In our next video, we'll be taking a look at the very last section of Chapter 1, which is Section 1.11, in which we'll regard a couple higher order differential equations that turns out that we can still solve using the methods we've developed thus far.